Sure. Thank you.
Okay. Hi, everyone. Good day. Good morning for me. I apologize if I'm a bit slow at speaking at times. For me, it's still quite early, and I kind of woke up not too long ago, but I'll try to make sense. And if I don't, or if you have any question, don't hesitate to unmute and ask questions as we go. So thank you for having me. I'm glad to have a chance to talk to you about some of the research I do, and I will focus specifically on the P-alpha survey for Pulsar conducted with the Arecibo, or really was conducted with the Arecibo telescope, which is really what I work most on. Okay, right, so I will so I don't know how, what is the, how people are familiar with pulsars and fast transients in general that are attended this seminar. So I'll just give brief descriptions of what these kind of objects are. And then I will describe the P-alpha survey, some of the most recent discoveries made by the survey. And then I'll move on to the observed population of pulsar, what we've learned in terms of the general population from the P-alpha survey, and also any hints of biases that we are seeing for P-alpha and the population of radio pulsars in general. So first thing first, neutron stars. We can't talk about pulsars without talking about neutron stars first. So neutron stars, they are the remnant of massive stars that died in supernova explosion. They're really dense objects, so they have mass about 1.5 solar mass and a very small radius, approximately 10 kilometers. So that's somewhat equivalent to the city of Barcelona. And so those mass and radius, it gives them supranuclear densities, which are interesting object to study. They make interesting laboratories when we want to study physics at extremely high densities. They also have high rotation rate. The fastest spinning neutron star that we know of has a spin period of 1.4 milliseconds, so that's about 700 revolutions per second. And the slowest that we know of is about 23 seconds. They also have the strongest magnetic field we observe in the universe, ranging from 10 to the 8, 10 to the 15 Gauss, on average 10 to the 12. So they are really the universe's strongest magnets. Now, radio pulsars are really the most common way to observe neutron stars. So neutron star, they produce, most of them produce radio emission, which is magnetospheric in origin, produced by the synchrotron emission as charged particles are being ripped from the surface and dragged along the magnetic field lines. There's going to be synchrotron emission in radio. So at the magnetic poles, you get a beam of radio emission. Sometime also in the magnetosphere, there's going to be higher energy emission, X-rays, gamma rays mostly. But really, radio is the most common type of emission we see from neutron stars. It's also possible to get sometimes thermal emission in the X-rays when you have hotspot at the surface. And NICER relies on that specifically to observe neutron stars. So to see a neutron star as a radio pulsar, you need the rotation axis to be, or you need the magnetic axis to be misaligned with the rotation axis, and you need that magnetic axis to point towards the Earth at some point. So it needs to cross, the radio beam needs to cross our line of sight. And this is how you get really the pulsation. So from Earth, if a radio beam from a pulsar passes our line of sight, we detect a short pulse. and this is why they're called pulsars. Most of radio pulsars are detected via periodicity search, so either in the Fourier domain with fast Fourier transform or in the time domain with algorithm like the fast folding algorithm, which is pretty new. The use of that algorithm is pretty new in pulsar searching, and this is also something I've worked on. So if you have any questions about that, you can ask me. And what makes pulsar a really useful object when wanting to study physics in the universe in extreme conditions is because their period and also the evolution of their period is measured with very high accuracy. So general 1 part in 10 to the 15 or better. So that makes them really exquisite cosmic clocks. So that's really what enables the wealth of experiments and studies that we do with pulsars. So at this point, we know approximately 2,600 radio pulsar in our galaxy. There are also some in the large Magellanic Cloud, small Magellanic Cloud, globular clusters, but really the bulk of the known population is in the galaxy, and most are focused on at low latitude in the plane, so in the disk of the galaxy, and that is because that is where the progenitor of neutron stars are born. So far, so good? Yes. Before moving on to fast transient, there's a concept that is really important and is going to be really important for the rest of the talk. And this has to do with how we observe radio pulsars. So as a pulse from a pulsar, which really is a packet of radio photons at various radio frequencies, as this pulse propagates in the interstellar medium, it's going to encounter ionized plasma. And it's really as that pulse interact with the electron in that plasma, there's going to be a chromatic dispersion of the radio frequency within the pulse by the interstellar medium. And that really follows the dispersion relation for plasma. And for when we study radio pulsar, we parameterize that dispersion with a parameter that we call the dispersion measure, or the DM, which is really the integrated column electron density along the line of sight between the observer and the source. So what happens when the pulse propagates in the plasma is that the lower frequencies will be delayed with respect to the higher frequencies. So the pulse, the different photons in the pulse will not arrive at the telescope at the same time. So you would get the higher frequency first and then the lower frequencies. And we know exactly how that time delay is gonna evolve as a function of observing frequencies, and the longer delay you have, the higher the DM is. So whenever we search for pulsar, we have to consider their DM. So we need to search blindly for various values of DM. And one thing that is very useful for us, radio pulsar people, are models of the electron density in the galaxies. So we can use then the DM of a pulsar, which is roughly constant. We can use their DM as a proxy for distance. So here, for example, we have the most commonly used electron density model, the NE 2001 model. So if here we have galactic longitude, so if you look at various galactic longitude And this is strictly for the plane, so at a latitude of 0 degrees. If you look at different longitudes, there's going to be a maximum amount of DM that is being contributed by the galaxy. So if you look directly, for example, directly at the galactic center, the maximum DM that you can get from our galaxy is roughly around 3,000 DM units. So if you know, if for example, you have a pulsar that is right on in the plane, and you know its DM, you know basically how far it is between us and the edge of the galaxy along that line of sight. So here on this plot, so we have for latitude of 0 degrees, and we have all the pulsars plotted here with their DM. But they are, for example, here, this dot is not necessarily outside the galaxy because it might not be at latitude 0. But this is the idea of how we use DM as a proxy. Also something that kind of appeared as people were searching for radio pulsar are fast transients. Fast transients, they are, when I say fast, I mean transient that are a few milliseconds in duration. So approximately the observed duration of a pulse from a pulsar. So we call them a single pulse detection as opposed to a periodicity detection. And there are two main types of source of fast transient. The first are rotating radio transients, or RRATs. And these are simply galactic pulsars that have very sporadic emission of individually detectable pulse. So, and this is true for any pulsars in general, there's a pulse-to-pulse variation in the intensity of the pulse. So one pulse to the next is going to be different in terms of intensity and also pulse morphology. So the RATs are just the extreme case where most of the pulse are not detectable with our telescope, but once in a while it's going to emit very bright pulse that we can detect, and we can't find those RRATs via periodicity search, because even the strong pulse are not going to come off at periodic interval. So we really need different type of algorithm to search for individual pulses. And then there are fast radio bursts, which really observationally are very similar to RATs. There are no major difference, same type of pulse duration. And fast radio bursts are fairly new type of astrophysical phenomena. So the first one was discovered in 2007, and it was kind of by accident. And now really when we search for our RATs, that's when we find fast radio bursts. So, and when I say new, the field of fast radio burst astronomy has really grew exponentially in the recent years. So prior to 2018, there were about 30 known source of FRBs. And now there are many hundreds. So people have really put time and resources towards searching for fast radio bursts. And these are really interesting because, as opposed to rotating radio transients, they are of an extragalactic, even cosmological origin. So we can detect fast radio bursts up to very high redshift. I think the largest redshift we know of is just below 1. And really the main difference between an FRB and a RAT is the FRBs has much higher luminosity. So they're intrinsically much, much more energetic. So that means that we can observe them from very, very far away. And we still, to this date, we still don't quite know what FRBs are. There are many theories, and actually even before 2018, there were more theories about what an FRB could be as opposed to the number of observed FRBs. No longer the case. But one of the really the dominant theories are those involving some type of extreme pulsars. And that would be because, well, it's very similar to the RRATs that we observe in our galaxy. And also you need some type of compact object to emit very short pulsations. So here on this plot, I'm showing the for the different morning. Right. So when we detect a pulse, to know whether this pulse is galactic or extragalactic, we look at how the DM of that source compares to the maximum galactic DM along that line of sight that is allowed from the galaxy. And we will classify a pulse as an FRB if it exceeds the maximum galactic DM. So here at the gray zone here is kind of the approximate, the approximate maximum, here at when you have a DM ratio, so your DM over the maximum galactic DM along that line of sight, that's when you have a ratio of 1. So anything beyond the galaxy, we classify as an FRB. Anything below that as an RRAT. And really, there's really a gray zone, and that gray zone can be even larger. Sometimes it's just beyond the galaxy, and the galactic electron density models are not, that accurate. They can be wrong by a factor of a few. So we always have to be careful when we find things that are kind of really borderline. But yes, this is how we distinguish FRBs from RRATs. Okay. Any questions? No? Okay, so going back to pulsars, probably the most important diagram that pulsar astronomers use is what we call a PP dot diagram. So the P is spin period, and P dot is the rate of change of the spin period of the pulsar. And those are the two pulsar parameters that are most easy to measure. So to measure the rate of change of the spin period, so the P dot, you need to monitor the pulsar over a few months, years. But those are going to be the first parameters that you measure. And what is very important with that diagram and those two parameters is that they can give you rough estimates for some of the basic properties of the pulsar. And that you need to assume that the pulsar is a magnetic dipole and that it rotates, which is pretty an accurate assumption. So there are three main properties that we can extract from just the period and the P dot. So the first one is the spin down energy loss, or we also call that the spin down luminosity. So that is the amount of energy the pulsar is giving off due to magnetic dipole radiation. And that is really kind of what creates a P dot. So over time, pulsar, as they rotate, they radiate energy away and they will slow down. So a pulsar would be born at some period, and as it loses energy, it's going to go down to longer periods because of that P dot. So the rotation of pulsar decreases with time. So we can measure the amount of energy that the pulsar is giving off. And also we can get rough estimate of the magnetic field at the surface of the neutron star, simply using the period and p dot. And also we can get a rough estimate of the age of the pulsar. So here on this plot, we can really visualize the magnetic field and the approximate age or characteristic age, just using P and P dot. So in green, we have lines of constant magnetic fields, and in salmon pink, we have lines of constant age. So a pulsar will go down in time, so to lower, to older age, larger age, and they will follow lines of constant magnetic field. And when we plot here the observed population of pulsars, we see different kind of cluster emerge. So the first one really is are the young pulsars, and those tend to emit high energy photons, and that is because their E dot is high, because the P dot is large, so the spin down luminosity is high. So we have the young pulsar that are, so pulsars are typically born in that area, and they will go down towards the lower right corner. Also, we have a small group of objects on the top right corners. Those are called magnetars. They are the largest, they are the pulsar that have the highest magnetic fields. And here, the energy is mainly lost, not due to magnetic dipole, dipole radiation, but it's the origin of their energy loss is mostly the decay of the magnetic field. They have very large magnetic field. So what happens with magnetars is that they are born with really high P dot, and they will slow down very rapidly. So they will have very long period, right. They're quite rare, and usually they're not very common in radio. So most magnetars are observed in the X-rays. And so in black here, we have the bulk of the population, the radio pulsars. And we also have another group of objects here in the bottom. Those are the recycled pulsars. They are the really old and low magnetic field pulsars. And just to talk a bit more about millisecond pulsar, because they are going to be quite central for the rest of the presentation. So those pulsars are formed when you have an old pulsar in a binary with their various type of companions to those binary system. But as a pulsar becomes old, their companion evolves, and there's going to be accretion from the donor star onto the neutron star, and that will cause the pulsar to spin up. Usually we can see X-ray emission from the accretion, and during the accretion, there's no radio emission. And also for most recycled pulsar, we think that they were, before the accretion started, they were really old and had very low spin down luminosity, and they were no longer emitting in radio. So they were kind of really dead. There's kind of that area here where there's no pulsar, and we call that the graveyard, or really like we expect a death line somewhere where if a pulsar goes beyond, the E dot is going to be too small to emit any type of energy. So we think that they are kind of old pulsars that were revived through the accretion. So as matter gets accreted onto the neutron stars is going to be a transfer of angular momentum. The pulsar is going to spin up, and also this rotation is going to become very stable. And that's because during the accretion, it also lowers somehow the magnetic field of the pulsar. So it's going to become very stable, has a very short spin period, and very stable rotation, so very low p dot. The fastest known recycled pulsar has a spin period of 1.4 millisecond, and they all have spin periods roughly below 100 milliseconds. So for that reason, we call them also millisecond pulsars. One thing that is very important, an important characteristic of millisecond pulsar is that they have very high fraction of binarity. So about 80% of the MSPs we find are in binaries, as opposed to 1 or 2% for the normal population of radio pulsar, where we think that most of the pulsar where they were most likely born in a binary, because that's what massive stars in the galactic plane do. And the supernova that gave birth to the neutron star disrupted the system. So when we observe a radio pulsar, they're typically isolated. But for the MSPs, most of them are in binaries, and the most common companion that we see are white dwarfs. So basically, for progenitors of MSP's system, you have normal stars. So the stars that give birth to white dwarfs are the most common stars. So as they evolve, after a very long time, the pulsar is very old. As they evolve, there's going to be Roche lobe filling, going to create an accretion disk. And once the accretion stops, the donor has become really just a white dwarf. And when the accretion stops, then the radio emission can get reactivated because the E dot has become sufficiently large. And that is because the period is very, very small. Millisecond are probably the most useful laboratories in terms of pulsar astrophysics. And that is because of their very, very stable rotations. They have served as testbed for testing theories of gravity, and were actually the PSRB 1913 plus 16, also called the Hall-Sale pulsar, was discovered with Arecibo in the 70s. That was the first proof of the existence of gravitational wave, and it kind of launched our effort to detect gravitational wave. They are also being used in an effort that we call pulsar timing arrays. So this is a different type of gravitational wave detector. It's on a really galactic scale. And the concept is to use the most stable millisecond pulsars, so the best cosmic clocks that are out there, use them as a sort of galactic GPS system, and try to detect stochastic gravitational wave background. So the very low frequency gravitational waves. And they were really starting after this project has been going on for over 10 years, and they are now really starting to place interesting limits, and yeah, it's really going well. So millisecond pulsars are really critical for pulsar timing arrays. Also, because most of MSPs are in binaries, that means that once in a while we're going to find system where you need to go beyond the general Keplerian gravity. So you need to consider relativistic effects. And when that happens, that's when you can get mass measurements for the neutron star. And that's very important for constraining the equation of state for supernuclear densities. There are also other things that we do with MSPs. NICER, for example, which is an instrument on the International Space Station that is doing surface mapping in the X-rays of neutron star, and that is to obtain radius measurements. So if you have, say, MSP in a binary and you are able to get a mass, and then if you then are able to get a radius measurement, that's when you really, really constrain the equation of state. They're also interesting for binary evolution purposes. For example, we found MSPs that are highly recycled, but are in an eccentric orbit, which didn't quite make sense with our idea at the time of binary evolution, because we think that circularization of an orbit is one of the first things that happens. Also interesting for accretion physics, and because the pulse are so short in duration and they're so stable clocks, we can study variation in their dispersion measures, like very small variations. And that tells us about the structure and the turbulence in the ISM as the pulsar is moving in our galaxy and as we are moving in our galaxy. Okay. That was kind of my intro to pulsars and fast transient. So now we can go into surveying and really how we find these pulsars, and specifically with P-alpha survey. So when you perform a large-scale survey for pulsar, as opposed to a targeted search for pulsar, there are different things that you need to consider when designing your survey. The observing frequency, in what radio frequencies you want to observe, the resolution also of your data, both in terms of frequency resolution and time resolution, because time and frequencies, they have to be sampled discretely into channels and time samples. The integration time, so how long you want to look at one position on the sky, and also where in the sky you want to look at. And of course, then there's also the main parameters, the telescope parameters, so the collecting area, the efficiency of the telescope, and also the configuration of the beam. So whether you're using only one big beam on the sky or multiple beams. And here is just showing different survey for pulsar and the area they target on the sky. And we'll talk a bit more about that. So just to go a bit more in details about those parameters, for the observing frequencies, most pulsar surveys are observing somewhere between 100 megahertz and 2 gigahertz. So when you choose your central frequency where you want to observe, you need to take into account that pulsars have power law spectra, and that their spectra decline very steeply with increasing frequencies. So pulsars are brighter at lower frequencies. Also, the beam, the size of the beam that you're observing the sky with, it also reduces with increasing frequencies. So if you go to lower frequencies, you can have a bigger field of view. But also the propagation effects are more severe at lower frequencies. So the plasma dispersion is going to be stronger at lower frequencies. And if you're, because the frequency, the band in frequencies that we're observing is sampled discretely, then if you're going to too low frequencies, you can have dispersion of the pulse within a channel, and you can't correct for that. So that's one of the downside to going to lower frequencies. And then there's the resolution. Higher resolution is just better in general, better to excise radio frequency interference, so man-made signals, which is a big problem in radio astronomy. And you're also you have also a greater ability to mitigate the effects of propagation, so the plasma dispersion. But searching radio data is very computationally expensive. So for P-alpha, for example, just processing one beam take at least 3 days. So higher frequencies, it's better, it's more sensitive, but you need the resources to do it. Integration times, so obviously the longer you integrate over a certain position on the sky, the more sensitive you're going to be to not only faint pulsars, because you're accumulating signal, but also to slowly rotating pulsars. So you're going to be, by looking longer at one position on the sky, you're going to collect more pulse from a slow pulsar and therefore increase the signal to noise ratio of your detection. However, if you have pulsars in binary system, especially MSPs in compact binary system, if you integrate for too long, then you're going to lose sensitivity to those systems, because we can actually detect a Doppler effect in the observed spin period of the pulsar. So that spreads basically your power in your Fourier spectrum. So if you go to too long integration, you're really losing sensitivity to compact binaries, and those are the really rewarding and interesting systems. And then, of course, there's where you want to look in the galaxy. So most pulsars are in the galactic plane, so that's where the first place you would want to look at. But the galactic plane also has a higher electron density, and the sky temperature is higher there. So the sky is brighter there, and propagation effects are going to be more severe. So the plane is not where you want to look necessarily if you have a survey operating at low frequencies. You would need higher frequencies to go there, to go in the plane. But if you're looking away from the plane where we don't expect that much DM, that much plasma, then you would want to go to lower frequencies where pulsars are brighter, so you can go far. Okay, so now the P-alpha survey. So that's a survey conducted with Arecibo. It started in 2004, and it observes at higher frequencies, so 1.4 gigahertz. It ranged from 1.2 to 1.5 gigahertz. In the survey, we have very high data resolution. So we sample every frequency channel, every 64 microsecond. And in terms of pulsar surveys, that's high frequency. So processing P-alpha data is very computationally expensive, but we have the resources to do it. So we have a lot of resources on supercomputer here in Canada. Fortunately, the operation at Arecibo stopped in August 2020 when one of the cable broke, and the telescope eventually collapsed in December 2020. So that completely put an end to the survey. But at least at that point, we have completed about 90% of the survey. So we were expecting to finish within a year or two. So not too bad. We can still, say something about the survey being nearly complete. Right. In terms of beam size, so here alpha is the name of the receiver we use for the P-alpha survey. It's a 7 beam pointing. So each of these 7 beams, they are collecting data and can be processed independently and must be processed independently. So whenever we look at one position on the sky, we will search each beam separately. And this is compared to other ongoing surveys for radio pulsar. Here you have the Parkes multi-beam. So with Parkes is a much smaller telescope. So the field of view is going to be bigger by default, and has 13 beams. GMRT and GBT 350, those are other surveys at lower frequencies and have larger field of view. So because with alpha, we have small beams. They are about 3 arc minute across, and for radio, in radio astronomy, that's pretty small for a single dish radio telescope. So when you have small beams, then you need more time to cover the region of the sky you want to survey. But we were lucky enough to have all the time we required with Arecibo to do the survey. It's also not optimal for searching for fast radio bursts, because while they are pretty common in the universe, it's unlikely that you will detect a fast radio burst from one small, if you have a small position on the sky, it's unlikely you're going to detect it. So to detect fast radio bursts, the strategy is to go with large field of view. So P-alpha is not optimal for searching for fast radio bursts because of those small beams. So for the survey, we look at 2 different parts of the galaxy. We stay strictly near the galactic plane, so we don't go beyond 5 degrees of the galactic plane. And we look at the 2 regions that Arecibo can see of the plane. So we have an inner galaxy and an outer galaxy. For the inner galaxy, we integrate each sky position for 4.5 minutes, because we want to maintain sensitivity to binaries. And also we can go to high integration if we want to eventually survey all the region we're targeting. And the outer galaxy is only 3 minutes, because this is actually data that observation that we share with another project, another group that are doing something totally different, but we need the same type of data. So those are commensal observations. And to date, we have discovered 208 pulsars and redetected many hundreds of known pulsars. And 46 of our discoveries are MSBs, which is actually more than we expected to find with the survey based on population studies. Really, the strength of the P-alpha survey is the large collecting area. Arecibo is just a huge telescope. So that gives us really a unique sensitivity to faint sources, even if we're higher frequencies where pulsars are already fainter. And we can also probe deep in the plane. So the higher frequency of the survey and the very high sensitivity of the telescope, we can really look to great distances. Here it's also shows the surveyed region, but from a top view of the galaxy. Here we are the yellow dot, and this is the inner region, the inner galaxy region we are surveying, and this is the outer one. Each white dot is a radio pulsar, and the green dots are the ones discovered by P-alpha. And here I'm showing the pulse average flux densities of the pulsars. It's an histogram distribution of the flux density, so really the brightness of the pulsars. And in blue are the P-alpha discovered pulsars, and in gray is all the other pulsars, all the pulsars discovered by other large-scale surveys. And we can see that really, in general, P-alpha is finding much fainter pulsars. Here is the distribution of their distances if we estimate the distance from their DM using galactic electron density models. And we can see that P-alpha is really discovering a population of pulsar that is very distant and far and faint. And again, stop me if you have any questions. Okay, some of the most exciting discoveries made by the survey. So there are the survey has discovered 3 double neutron star systems, and double neutron star system are really the most exciting type of pulsars that we want to hunt for, because then that's where general relativistic effects are going to be strongest, and that's where when you have the best chance to make neutron star mass measurements to constrain the equation of state. So 3 years ago, we found the double neutron star system that had the shortest orbital period. It was only, probably called 2 hours orbit, and also had the shortest merger time. So it's expected to merge in 46 million years. So that is important for predicting neutron star merger for gravitational wave observations. And also a really new result on J1913 plus 1102. So this is the double neutron star with the most asymmetric mass ratio. So the mass ratio of the 2 neutron star is 0.78. And that's fairly uncommon. And it's actually, it helps, or it provide an explanation for the strange or unusual, unexpected properties of the gravitational wave neutron star merger JW 170817, which had a really large ejecta, and having an asymmetric mass ratio like J1913 could explain a large ejecta for a double neutron star merger. And even more new result, we haven't published that yet, but we found we believe we found 2 new double neutron star systems. So in the galaxy, including those 2 new systems, we know of 19 double neutron star systems, and in total 5 were discovered by P-alpha. So the 2 new systems, they have orbital periods of 2 and 9.5 days. Just looking, I'm doing on time, not so good. Okay, I'll try to speed up. They have, in terms of, as far as double neutron star systems go, they're not so compact systems, so they're not relativistic in a sense. They're not going to merge in Hubble time, but they're still good candidate for mass measurements. And our early result, we've been monitoring those pulsars for a few years now, and one of them could potentially be the lowest neutron star, the lowest mass neutron star that we know of. And here I'm just showing basically the eccentricity is one thing that is commonly seen in double neutron star systems. So while most, say, millisecond pulsars, they are observed in circular orbits, when we have eccentric orbits, then that's when we're most likely to find double neutron star system, because you had kicks from supernova 2 times. So eccentricity is going to be higher. And just as a function of orbital periods, so they're kind of the lower eccentricity, longer period, orbital period side of the population. So not as relativistic as others. And here it's eccentricity versus spin period. Also, FRB's discoveries. So recently, a few months ago, we found a 3rd source of FRB for P-alpha. So P-alpha has discovered 3 FRB now. The first one in 2014 was FRB 121102, probably the most famous FRB of all, because FRB 121102 was the first repeating source of FRB. So usually FRBs are one-off event, but in 2016, as we were following up the only then FRB discovered by the survey, we found repeats, and that was the first time we've seen any repeats from an FRB. So that meant that whatever mechanism was producing the FRB need to not be cataclysmic. So you need to, so for example, before then, we thought of mostly of supernovae, double neutron star merger, or compact mergers, those kind of theories to explain FRBs. So you get a very big amount of energy and you get one burst and then that's it. But when we found repeats, that really kind of changed the games, and you need to think of a mechanism where the progenitors are stays alive and well and can produce more repeats and also have a big energy reservoir. And then 2 years later, in 2018, we found FRB 141113, which is the faintest or the lowest luminosity FRB known. And that one was important for constraining basically the energy distribution of FRBs, which is important if you want to understand the origin of FRBs. And yes, last summer we found the third FRB, and that one was just slightly brighter at detection than FRB 121102. So here I'm just showing, this is all the published FRBs at their L-band. So L-band is around 1.4 gigahertz, or all frequencies. That includes lower frequencies. So CHIME is an experiment that is looking for fast radio bursts. It's a new experiment and it's found hundreds of FRBs. It really just changed the game. So it's finding a lot of FRBs. So here we have the distribution of the energy of these FRB source. And we see the one in orange are the one found with P-alpha. So that is the one we found in 2018. So it's really the faintest or the lowest energy FRB. And the newest discovery is around here, so just a bit brighter than 121102. And yeah, that's FRB. And also we are preparing a paper we're preparing to release measurements of P and P dot. So the result of long-term monitoring of more than 85 pulsars. And some of them are really interesting and also helps constrain different things like in terms of energy emission mechanism. So that's also coming. All right, how much time left?
Maybe you can wrap up soon so we have some time for like a few questions at the end. That would be great.
Okay, so now moving on to the observed population, which I'll do really quickly. And again, we can talk, I know a lot of you must be interested in that. So we can talk later about this, but there are different reasons why you want to characterize the population of neutron star you observe. It helps to really better understand what kind of progenitor could create a gravitational wave event, FRBs, and other really energetic transient, because neutron stars are such excellent reservoir of large amount of energy. You also want to understand the birth and evolution of neutron stars. So you want to link the different kind of class of neutron star that we saw in the PP dot diagram. Also MSPs are high energy emitters. So they might provide an explanation for the gamma ray excess that we see on the galactic plane. And, but also just knowing what it is you're observing and identifying biases in the surveys, it helps you make better surveys for the future. There are different things that will affect the population you are uncovering, and I'll focus really on those that touch on survey design. So the central frequency that you're observing with is going to create bias in the observed population, and it's not quite as expected. So here we have the number of the distribution of pulsar based on their DM derived distance for different frequencies. So the high frequency in gray and purple and orange for the lower frequencies. And while normally you could use lower frequency to probe faint pulsar, which are brighter at higher frequencies, at lower frequencies, we are actually probing greater distances at higher frequencies. And that could be really because you're less affected by propagation effect. We are also seeing observational bias in the DM and period distribution of the pulsars based on the central frequency we're using. So actually, for example, the shorter pulsars are more easy to discover at using higher frequencies compared to lower frequencies. And that's not that surprising because at lower frequencies, there's more smearing of the pulse because of the plasma dispersion. So by default, a pulsar with a large or long duration pulse or a slow pulsar would be less affected by DM smearing. And also for P-alpha, something that we didn't necessarily expect is that we found a lot of really fast spinning MSPs at high DM. And those are generally the most challenging object to detect because of very fast spinning MSPs have very small duration pulse. So they're going to be more vulnerable to propagation effects, so plasma dispersion. So finding the shortest spin period and highest DM ones is really what is the most challenging. And we can see that P-alpha is really helping in finding those type of pulsars. And they're also, because we're targeting the plane, that means we're really finding the high DM in the plane MSPs. And that's an important object to find if we want to understand the gamma ray excess in the plane, but also just have a better modeling of the known population. Right. I'm going to skip that because we're running out of time. So, right, just to summarize, so there were also signs that also in terms of binary MSP population, P-alpha is also uncovering the compact, fast spinning pulsars, so the most recycled objects. And right, and we need surveys like P-alpha, so surveys that have the sensitivity of P-alpha. The frequency is also the same survey design of P-alpha, but we need to go to a wider range of longitude because P-alpha only targeted a limited range of the disk. And there were also hints that high emission or searches that are directed by high energy emissions, so Fermi sources that are unidentified. If you go and take radio telescope and you look specifically for that for a long time, so you're totally different than large scale surveying, but this is also efficient at detecting MSPs. So that is an alternative to a large scale survey that should be pursued. And right, so despite pulsar being much fainter at higher frequency, P-alpha is really finding the faintest pulsars and the very distant one. We found more short of the short spin period and high DMSPs than we expected, which tells us something about the population and how many there are those kind of MSPs in the plane. It's also the most efficient survey for finding double neutron star systems. And right now we are reprocessing older data with a searching pipeline that has a higher sensitivity to binary acceleration, slow pulsars, and also RATs and FRB. So we might have more discoveries coming. And I'll just leave that there and take any question. Sorry for going over time. But...
Thanks very much, Emilie. Are there any questions from the audience? I have Sinanda raising her hand.
Yes, so thank you very much for the very nice presentation, very clear. My question is related to the, you didn't, and I missed, the biases you might have for slow pulsars. So how, somehow, which are the bias and why are those biases, and which is, let's say, the slowest pulsar that you think you might be able ever to find there?
Right, and that's a very good question. It's also very important for magnetars when you're searching for magnetar in radio. So because there are very few magnetars, slow spin periods that are loud in the radio. So you want to look for those. That will tell you a lot about emission mechanism. So in theory, if you have a perfect survey, if your data is, if the noise in your data is Gaussian, you're gonna have the minimum flux density that you can detect with a survey like P-alpha. It's gonna be the black line here. So it's flat. Your Gaussian noise, you would detect any of the long period pulsars. But noise in radio data is not Gaussian. There's red noise, so there's fluctuation in the gain of the telescope. So it's really the effective sensitivity of the telescope. Also just system temperature fluctuations in the instrument, and that will cause kind of long baseline variation in your data. And that makes specifically slow pulsar searching difficult. Also RFI, just generally, if you're, say you have data and you're folding data at a short spin period, it's easier to kind of blend in RFI, so you're going to be less affected by RFI. But for slow pulsars, RFI is just really a bad, just badly affects your sensitivity. And yeah, man-made interference is it's just gone so bad in the recent years. So red noise and man-made interference really changes our sensitivity. It changes from the normal radiometer sensitivity that you would expect from a radio, and it will instead follow these curves. So in the dotted lines here are the result of an injection simulations where we took the P-alpha data, we injected slow pulsars in them at different values of DM, and we tried to recover them, and we looked at what was the minimum flux density we could detect at different periods and DM values. And with an FFT search, those are the lines that you get. So you're really going away from radiometer the longer period. When you go to longer period, you're really going away from the radiometer. So one thing we did to mitigate that is to use a fast folding algorithm. So where instead of going the Fourier domain, you stay in the time domain. And when you do that, the advantage is that you're keeping all the power that is in harmonic, you're adding them coherently. So you're not losing any signal as you would do in the Fourier domain. And doing the same type of injection analysis, we saw that we could recoup some of that sensitivity loss due to RFI and red noise, but not all of it. We're still far away from the radiometer. And so actually, since we implemented this algorithm in 2017, there was only 2 pulsars that were missed by an FFT, but detected with the FFA. So for P-alpha, there might not be, or the part that we're targeting either, we need even better than an FFA, or really integration time is just, yeah, or they're just not really many pulsars like that out there, which would kind of be surprising.
Okay.
But yeah.
Very much. Thanks.
Okay, there was another question from Guillaume.
Yes. Hello. Very nice talk. Hi. I have a question, something that you explained at the beginning. At some point, I was looking into this. It's about the dispersion measure and the electron density that it's used for the pulse dispersion and all this. Yeah, you can have it. But see, yes, there is this model that gives you the electron density in the galaxy, and that allows you to predict more or less what's your. So the question is, how well understood is this electron density, especially not the bubbles, because, for example, I think some bubbles are associated to star forming regions and peculiar things. But let's say the background, or let's say the galactic electron density, and how it is related to normal matter. Let's say, for example, could we say for each electron there is one hydrogen atom that it's flying around, or which atoms are there? Is it done? Because at some point, I mean, it has to be a relation, otherwise the universe would not be neutral. These electrons come from neutral atoms, or there's no neutrality, I don't know. But this has been thought, because there is also important physics, I think, there, that sometimes are not being deep enough. And these are very precise measurements. As you said, these measurements, with the pulses, you see all the structure in the electron density. So there is a lot.
So with the DM, it's really a precise measure, but we really don't know the distance. So when we produce these models, I didn't really look into that kind of analysis, or didn't do that kind of analysis myself, but they use different things. They use, extinction values from optical. There are different things that goes into it. But the DM really, if you have a pulsar, you really need a few, say, calibrators to really test if your model is right and kind of adjust it. So those calibrators are usually pulsars for which you can measure a parallax, and those are relatively rare. And when you're using too much of it, you're kind of overfitting. So no, I don't think that. I think it's more the other way around. I think the model is more based on what we know of, normal matter and the plasma in the galaxy from other type of studies, and they kind of build from there. So it's not much the other way around, but as we detect more pulsars that have parallax distances, then that's when we can kind of reverse the game and make better linkage between the DM and the distance, and then the matter itself.
Yeah, I mean, I'm just thinking because the charge is equally distributed in electrons and protons, but the mass is in the protons. And when we are estimating the mass of the galaxy and things like this, and also other galaxies, these electrons are contributing there. It has to be related somehow to the positive matter, let's say. And I haven't seen this connection done clearly in many places.
I can't.
Okay.
That, yeah.
Well, more pulsars, yes.
Yeah.
That.
Okay. Any final questions for Emilie? Then I will stop recording.